Assalamualaikum and hi. We continue our lecture this week into chapter 1, which is water purification in natural systems. So, if you refer to the textbook, this will be in chapter 1 in your book. This lecture note is a sequence from the previous recap lecture note that I gave to you last week. For this chapter, I'm going to split it into two parts, which is chapter 1 part 1 and chapter 1 part 2. Okay, from our previous lecture note, we learned that water resources come from three sources, which are surface water, groundwater, and rainwater. So, example of source from surface water are like lakes, rivers, and ponds, while from groundwater are like springs and wells. Example, the source from rainwater, besides from rainwater itself, it can be from snow melting. Before we go any further, we have to know what is meant by self-purification of the stream. For example, if wastewater is discharged to the river, the BOD of the mixed stream, which is the clean stream, will meeting with the wastewater stream, will initially increase and the dissolved oxygen will go down. However, when the water starts to travel along the stream, the BOD will start to decrease and DO increases, which gradually improving the quality of the water. This is what we call self-purification of the streams. It's like the river is self-cleaning itself. Okay, the processes involved to purify the water can be divided into three, which are through physical, chemical, and biological. In this lecture note, I will cover physical and chemical processes to purify natural water streams. Self-purification of the stream through physical process can be done through these 5 methods, which are dilution, sedimentation, filtration, gas transfer, and heat transfer. So I will be explaining these 5 physical processes throughout this chapter. Okay, these 5 physical processes is used by the stream to self-cleaning. Dilution is considered as one of the most economical solution to water pollution. It is a powerful self-cleaning mechanism to surface water. Okay, so dilution uses mixing zone concept. Okay, for example, the pollutants from the discharged water can be diluted when it's discharged into the large body of surface water. Okay, to know the capacity of the dilution, for example, the concentration of the pollutant after mixing with the discharged water, we can use the mass balance concept as stated in equation 3.1 in your book. Okay, for example, if you refer to this diagram, we can predict the concentration of the pollutant in point B, which is the point after wastewater discharge to the stream. Okay, so from this equation, you can see that S is actually stands for the stream. Okay, W is for the waste stream, while M is the that contributes to the mixture after the wastewater discharge into the stream. Okay, where in this diagram is in point B. So let's have a look in example 3.1. Okay, so from this example, we can see that wastewater enter the stream at a concentration of 250 milligram per liter and flow rate of 1.5 meter cube per second. Initially, the stream has a concentration of sodium at 10 milligram per liter and the flow rate is around 20 meter cube per second. So in this question, wants you to calculate the concentration and also the flow rate in point B, okay, which is after the point where the wastewater discharge meet with the stream. Okay, so if we use back the equation 3.1, okay, so you just replace the value insert the value into the equation, and then for QM, okay, QM is actually the flow rate of the mixing. Okay, this one from your mass balance knowledge, it is actually the sum of the total of your flow rate in the stream A plus the flow rate in stream wastewater discharge stream. So by right, the volumetric flow rate is actually 20 plus 1.5, so it will be 21.5. So, and then after inserting all the values, so you will end up having the concentration of sodium at point B, which is after the discharge water, is actually 26.7 milligram per liter. So the second physical process is sedimentation and resuspension, right? So what is sedimentation? Is removing suspended particles from watercourse. Normally, it is for suspended solid, so it will involve large particle size. So large particle will settle down, and then a collider particle also will take some time to settle down. However, all this settling down of the suspended particles, okay, will cause sediment accumulation, which in the end will develop banks of mud, and this will reduce reservoir storage capacity, and eventually it will increase flooding. Okay, so resuspension is common during flooding and heavy runoff. The third physical process is filtration. Okay, filtration in the stream is done by the small organic, which is pebbles, clays, along the stream bed to clean the water. Gas transfer is the fourth physical process, which is very important in natural water purification. This is because oxygen loss in the water will need to be replenished through gas transfer process. Okay, so at equilibrium point, the number of gas molecules leaving the liquid, as what described in the figure, is equal to the number of gas molecules entering the liquid. Okay, so we later will see that solubility and transfer rates are the two important water characteristics to describe the condition of the gas in the water. The solubility of gas in water can be described by Henry's law, shown by equation 3.2 in your textbook, where H is Henry coefficient, P is the pressure of the gas above the liquid, and X is the equilibrium mole fraction of the dissolved gas. And as what you have learned before this in chemistry, okay, the mole fraction of gas can be calculated using another equation, which is equals to moles of certain gas over the total number moles of total gas in the liquid, and also the gas. Example 3.2 from the textbook wants to calculate the solubility of air in water at 1 atm and 0 degrees C. So first, before we can calculate that, we need to calculate the mole fraction in the water, which is X. And we use the equation 3.2 just now. So the value of Henry's constant can be obtained from table C2 in appendix C, which is the value 4.32 10 to the power of 4 atm per mole fraction. So we substitute back in the equation 3.2, where P here is actually equals to 1 atmosphere. Okay, in order to calculate the concentration of air in the water, right, in this slide is CS, we need to determine first the mole of water. Okay. And then, therefore, mole of water is calculated by using the density of water divided by molecular weight of water, and you will get mole of water. Okay. So, here you will end up with 55.6 for mole of water. So, as we know that the mole fraction X is actually the mole of water divided by the total mole of water and also air. So in the end, you will get that the total number of moles for gas or for the air is actually 1.287 10 to the power of -3. Okay, so now we convert this mole to concentration by multiply with the molecular weight of air. So this is like a conversion unit that you wanted to find to convert it from mole per liter to milligram per liter. Okay, now we know that the component of air, we have nitrogen, oxygen, and also carbon dioxide. So nitrogen is 79%, oxygen is 21%, and CO2 is 0.3%. So you use the similar method as previously to calculate the concentration of the gases in the water. So again, you need to calculate X for every each of nitrogen, oxygen, and also CO2. So repeat back the method again. You determine first the Henry's constant from table C2 for nitrogen, oxygen, and carbon dioxide, and then you find the mole fraction of the gases. Okay, and then for the concentration of each gas, you times with the molecular weight of every gas. For instance, for nitrogen, molecular weight is 23.25. And then oxygen is 16, and CO2 is I think around 16, isn't it? Right? Okay, the second term that is important to characterize gas transfer in water is transfer rate. Okay, this transfer rate is very important in aeration. Okay, later you will see this again in purification through endemic system. In the next chapter. Okay, so based on the equation written here, transfer rate can be described as the change of concentration over time, and then is equals to Cs minus C over times Ka. Ka is actually a constant that depends on temperature. It's like Arrhenius follows like Arrhenius equation. And then it also depends on interfacial area and the resistance to movement from one phase to another. Physical processes is heat transfer. Okay, temperature of the water is very important for us to know, because we can treat it as an indicator. Because by increasing heat, the temperature will increase, and the decrease in the number of aquatic plants and animals. Okay, there's certain temperature that the allowable temperature for these aquatic plants and animals to survive at a certain temperature. Okay. So now I have fully covered the physical processes for the water to naturally purify. Okay. Okay, I will continue describing the chemical process in the next part of the video. Alright? So, okay, so I think I'll see you later in the next part of the video. Okay, thank you.